Hello, Chem 2 students. Mr. Keister here with you again today. This is the video for Monday, November 9th, 2020, which is our scheduled 56th, I think, day of school for the fall semester. Always keep in mind, though, that the dates could change for a variety of reasons, but the lessons and the order that those lessons are presented will remain the same regardless. So let's take a look at our schedule and see what the do now say for today. So today we're starting a new unit, Unit 4.2, which is over the nomenclature or naming and formula writing of ions and compounds. On Friday, we didn't have anything because we had an exam on Friday. In fact, the Unit 4.1 exam I have graded, and it's in the grade book already, so it's in Power School. The average in all three classes was in the mid-80s again, which is really quite good. Based on the amount of material that you had to know and all that drawing you had to do. A lot of you did very well. So good job. I won't be able to hand them back, though. I got a few students who haven't taken it yet, so I won't be able to get them back to you until that is done. So today we're going to begin Unit 4.2, which is a review over chemical nomenclature. Of course, you guys had nomenclature in Chem 1. We'll see how much of it you remember. The naming and formula writing of ions and compounds. Today we're going to start with monatomic ions, which are single atom ions, and then binary ionic compounds, which are the compounds that they form. You'll have an assignment over this that's due tomorrow. Special note, starting tomorrow, you'll see why having the polyatomic ions memorized. I had you do that last week. You'll see why that becomes necessary. You are going to need to know them as of tomorrow. So if you need to review them, I would strongly suggest that you do tonight. Okay? And another FYI, this unit is quite short. Plan on the Unit 4.2 exam being 1 week from today, which would be Monday the 16th of November, unless something changes with that. There's also another Mastering Chemistry assignment that is coming quite soon, so that'll be coming too. All right? All right, well, let's get rolling on nomenclature. So, monatomic ions and their ionic charges. So we've seen that in the formation of ionic compounds, neutral atoms can either lose or gain one or more electrons based on their electronegativity difference and the number of valence electrons they have. So a monatomic ion is a single atom that has lost or gained one or more electrons. Thus, a monatomic ion is no longer neutral and is either a positive or negative charge. We went through that last unit. A cation is a positively charged ion. It's been formed from the loss of one or more valence electrons. Cations are formed from metals. Right? Remember, metals have very few valence electrons. About 90% of them only have one or two. Right? And their electronegativities, as a rule, are quite low. And so they tend to lose electrons and form positive ions, or cations. Nonmetals, on the other hand, because of their much higher electronegativities, much stronger Coulombic force there, they form negative ions, all right, or anions, by gaining one or more electrons. They gain enough electrons, remember, to fill that valence p orbital, all right, to get it full like a noble gas. Recall that the charge on a monatomic ion can in many cases be predicted from the neutral atom's location on the periodic table. Remember, based on their group number. Group 1A metals, the alkali metals, lose their one valence electron and form positive 1 ions. Group 2A metals form positive 2 ions. Group 6A nonmetals form negative 2 ions. Remember, they have 6 valence electrons, they want 8, so they gain 2, and so on. All right, so let's look at the metals first. So metal cations in groups 1A through 6A are formed from the loss of one or more valence electrons from a neutral metal atom. Their ionic charge, all right, is the same numerically as their group number. Remember that. Their ionic charge is the same numerically as their group number. Their name is the same as the neutral atom's name, except for the word ion instead of atom. All right, so we have a sodium atom, we have a sodium ion. We need to know the difference. All right, you go to the next page there. So out of group 1A, remember they form positive 1 ions or just plus ions. And so again, sodium, we just said. So Na is a sodium atom, but Na plus 1 or Na plus is a sodium ion. All right, note the difference. Group 2A, they have 2 valence electrons. They lose those 2 and form plus 2 ions, or 2 plus, remember. So Ca is a calcium atom, while Ca plus 2 or Ca2 plus, again, I don't care how you write that, either way is fine by me. But remember, mastering, I think, prefers writing the number first, so I'd probably better write it 2 plus when you're doing anything with that in mastering. But anyway, Ca plus 2 or Ca2 plus would be a calcium ion. Aluminum's a metal in group 3A. It forms a plus 3 charge, so Al would be aluminum atom. Al plus 3 or Al3 plus would be an aluminum ion. Okay. Group 4A, lead. All right, so lead, Pb is a lead atom. Pb plus 4 is a lead ion. 5A, bismuth is a metal in 5A, so Bi would be a bismuth atom, Bi plus 5, a bismuth ion. And in 6A, polonium is a metal, so Po is a polonium atom, and Po plus 6 is a polonium ion. All right, so same name. Metal cations from the transition metals and intertransition metals are also formed from the loss of their 2 valence electrons. And in addition to that, as we talked about in the last unit, they can form a second or even third or more ion from the loss of their next most outermost D or F electrons. Their names are also the same as their neutral atom, but if they form multiple ions, we got to have a way to distinguish between them. And for that, we use a Roman numeral. So, for example, so Fe is an iron atom, but Fe plus 2, which is a transition metal and forms multiple ions, the plus 2 ion is called the iron Roman numeral 2 ion, or iron 2. Notice the Roman numeral is in parentheses, right? So hopefully you remember your Roman numerals, all right? Do you? Hope so. Let's see. So 1 is I, 2 is double I, 3 is triple I. Oops. 4 is IB. 5 is B. 6 is BI. And 7 is BII. So make sure you remember those. All right, make sure you remember those. So iron Roman numeral 3 is iron plus 3 or Fe plus 3. All right. So manganese, Mn is a manganese atom. Manganese actually forms 4 positive ions. So we have manganese 2 is Mn plus 2, manganese 4, Mn plus 4, manganese 6, Mn plus 6, manganese 7, Mn plus 7. So remember this. Very important. Roman numeral equals the positive charge on the transition metal ion. All right, the Roman numeral is the positive charge. Not how many of them are in the compound. That has nothing to do with it. It's equal to the positive charge. Now, there are 3 transition metals that only form 1 cation. Only 1, all right? And so for them, a Roman numeral is not necessary. So these you must memorize, all right? Ag plus, silver only forms a plus 1 ion, all right? Zinc and cadmium only form plus 2 ions, all right? So let's take a look at that real quick. Talk about zinc and cadmium first, all right? So here's zinc and cadmium. Zinc ends 3d10, cadmium 4d10. All right, so they're the last 2 metals in the D block in those first 2 rows. All right. So zinc has, of course, they both have 2 valence electrons. Zinc is 4s2 3d10. Cadmium is 5s2 4d10. with those d orbitals being full, all right, that's stable. So those two only lose their 2 valence electrons, hence they only form +2 ions. Now below them, mercury and capricinium, they form multiple ions. Now their d sublevel, their d orbital is full as well, but with a weak Coulombic force, you know, as you're going down the group, that Coulombic force gets weaker. They're able to have electrons pulled out of their d orbitals. All right. So only zinc and cadmium form a +2 ion. All right. Just those two. So, and then silver. Silver's right next to cadmium. Silver only forms a +1 ion. You're thinking, how in the heck can that be? All right. Well, so let's look at silver. So silver is, you know, 1s2, 2s2, ... And then we finally get to 4s2, 3d9. All right. Let's look where it is. 4s2, 3d9. You're thinking, now wait a minute. Or I'm sorry, 5s2, 4d9. My mistake. 5s2, 4d9. So you're thinking, how in the heck do we get a +1 ion out of that? Well, here's why. The 5s orbital and the 4d orbital are very, very close in energy. All right, very close. And so with 4d9, that d orbital wants to be full. So there's an exchange here of an electron between that 5s and 4d orbital. And so in reality, based on energy, all right, silver's actual electron configuration ends up 5s1, 4d10, rather than 5s2, 4d9. It's a more stable arrangement because that d orbital is now full. Well, that leaves silver then with one lone valence electron, 5s1, and that's the one it loses in forming a +1 ion. All right. So these 3 transition metals are the only 3 that only form one positive ion, and as such, no need for a Roman numeral. So you need to memorize those. All right. So Ag +1 is silver, Cd +2 cadmium, and Zn +2 zinc ions, respectively. All right, make sure you know that. Now, also, there are 2 regular metals, tin and lead, that although they are not transition metals due to their locations towards the bottom of 4A, with a weaker Coulombic force, they often regularly can form 2 different charges, +2 and +4. All right, so because of that, we're going to have to use a Roman numeral to distinguish between them, all right? So tin Roman numeral 2 or tin 2 would be Sn +2, and tin +4 would be Sn +4, all right? Lead 2 would be Pb +2, lead 4 would be Pb +4, right? Of course, or 2+ or 4+, all right? So make sure that you memorize those 2. So we have a couple of exceptions here. We have 3 transition metals that only form 1 ion, so no Roman numeral there. And we have 2 regular metals that can form 2 ions apiece. And so we do need a Roman numeral there. All right. Make sure you know those 5 exceptions. All right. So next, non-metal monatomic ions. Okay. So the nonmetals in groups 4A through 7A, excuse me, are formed from the gain of 1 or more valence electrons by a neutral nonmetal atom. Remember, nonmetals have stronger Coulombic force, so they have a much higher electron affinity, higher electronegativity. Their ionic charge is the same numerically as 8 minus the group number, because that's how many electrons they want to gain to complete their octet. So again, like group 5A has 5 valence electrons, they want 8, they gain 3, they form a -3 ion. Okay. Now here's something different about nonmetal ions in regards to their name. Their name is not the same as the neutral atom. Instead, only the basic root stem or beginning of the name is used, and we change the ending to an IDE ending. I, all right? So, for example, in 4A, C is a carbon atom, but C minus 4 or C4 minus is a carbide ion. We keep the beginning of the name, but we drop the ending ON and replace it with IDE. All right. Group 5A, N is nitrogen, N-3 or N3 negative is the nitride ion, okay, IDE. Again, we just keep the beginning part the same. We drop off the OGEN, replace it with IDE. Group 6A, O is an oxygen atom, O-2 or O2 negative is oxide, okay. Group 7A, F is fluorine, F minus 1 or F negative is the fluoride ion, all right? So metal ions keep their normal name, okay? Transition metals, we'll need a Roman numeral except for 3, all right? But they keep their normal name, but non-metal ions, anions, names change to IDE, all right? So remember that. Hydrogen. Since hydrogen only has one electron in its 1s orbital, then it can either lose, share, or gain only one electron when forming compounds. Normally, hydrogen shares electrons because of its electronegativity. However, it can, based on a sufficiently large electronegativity difference, form a positive or negative ion. It's fairly uncommon, but it can happen. All right. When it loses one electron and forms a +1 ion, H+, it follows the rule of the metals. All right. Normal name. So H+1 or H+ is a hydrogen ion. If it gains an electron from a metal, which it could if the electronegativity difference is large enough, and it forms a -1 ion, then you name it like you would any other nonmetal. Name changes to IDE. So H-1 or H- would be called the hydride ion. So H+ or H+1 is a hydrogen ion. H- or H-1 is a hydride ion. Okay? Next page. Polyatomic ions. All right. Well, we're going to hit those again tomorrow. Hard. So remember, monatomic ions only come from a single neutral atom. Okay, straight off the periodic table. A polyatomic ion, of course, has multiple atoms bonded together covalently. That as neutral compounds have a shortage. At least one of the atoms has a shortage of valence electrons, and so to be stable. Remember, we talked about this in the last unit. They form negative ions. Okay, so remember there's only one common positive polyatomic ion or cation, that's an ammonium ion, NH4+1 or NH4+. There are a lot of common polyatomic anions, and the ones used most often are in the handout that you've already supposedly memorized. Hopefully you still remember them. So we're going to work with those tomorrow. Remember that the polyatomic ions are formed from the covalent bonding between two or more nonmetals that results in a compound that is electron deficient, all right? And by gaining the number of electrons needed to complete every atom's octet, the polyatomic anion is then formed and thus becomes stable, okay? All right, so let's look at naming and formula writing or nomenclature of ionic compounds. So today we're going to look at binary ionic compounds, which are compounds that contain ions from only two different atoms, all right? A cation from a metal and an anion from a nonmetal, all right? As we learned earlier in our unit, these ions combine by transferring electrons and do so in such a way that all ions complete their octet. In every case, the positive and negative charges always balance out to 0, all right? So that the exchange of electrons happens such that each atom achieves their octet, which is going to result in the formation of positive and negative charges for each of those ions that then balance out to 0 overall, all right? So let's advance the page here. In naming a binary ionic compound, all right, the cation's name is the same as the neutral atom, all right? Remember, same, except for the Roman numeral in tin or lead, or a Roman numeral in most transition metals, except for the 3, and it's named first. So positive ion, metal name first, negative ion, anion, the nonmetal name, which ends in IDE, is named last. All right, is named last. All right, so let's take a look at that. So here we have KBr. All right, so KBr, K is the metal, keeps its normal name, that's potassium. And Br is the nonmetal, its name changes to IDE, which would be bromide. So KBr would be potassium bromide. All right. Next, MgO. Okay, so magnesium is the metal, normal name. O, the nonmetal, changes to IDE, so that would be oxide. Magnesium oxide. Al, aluminum's our metal, normal name. Fluorine, our nonmetal, changes to fluoride. Now, hopefully you remember. Now, why is it KBr, not KBr2 or KBr3 or K2Br? Think about when we were doing ionic bonding. Okay, K only has one valence electron, wants to lose one. Bromine has 7 valence electrons, wants to gain one. Lose one, gain one. They combine in a 1-to-1 ratio. That's KBr. All right. So why is it AlF3? Well, Al wants to lose, has 3 valence electrons, it wants to lose them, so it wants to lose 3 electrons. But fluorine, with 7 valence electrons, only wants to gain 1. So they're not going to combine in a 1-to-1 ratio. You're going to need 3 fluorines for each aluminum, so it's a 1-to-3 ratio, hence AlF3. All right. We did all that when we did bonding, so there's really no reason to do that again. Hopefully you realize that just from valence electron situation. So Na3N. Na is sodium, that's the normal name for the metal. The nonmetal N would become nitride. AgCl. AgCl. Okay, well, let's look at that one. All right, so AgCl. Ag is silver, that's a transition metal. Normally, they require a Roman numeral, but silver is one of the ones that doesn't. Remember, it only forms a +1 ion. And so this would just be silver, no Roman numeral. Cl, of course, the nonmetal would become chloride. All right. But now I'm going to put a little star by these two because iron is a transition metal that does require a Roman numeral. All right, it does. Well, let's look at that. Iron keeps its normal name, of course, and O becomes oxide. The next one, Fe2O3, also involves iron and oxide. Well, you can't call them both iron oxide. You know, which one you're talking about. This is why the transition metal needs a Roman numeral, all right? So let's look at the charges here. What is the charge on oxide? Well, O is in group 6A, wants to gain 2 electrons, it's -2. So in FeO, if O is -2 and there's only one Fe to balance that -2, what's the charge on the Fe? Remember, they add up to 0. Well, it'd be +2. If the charge is +2, then the Roman numeral is 2. Remember, Roman numeral equals positive charge. All right? All right, so let's look at Fe2O3. Well, once again, O is -2. But there's 3 of them. All right, there's 3 of them. So the total negative charge in that compound is -6, which then means the total positive charge in that compound is +6. Well, there's 2 irons in there. So if the total positive charge is +6 and there's 2 of them, then each of those irons has to be +3. There's 2 of them, but each one of them is +3. If the charge on the iron is +3, then it's Roman numeral 3. So it'd be iron 3 oxide. So FeO is iron 2 oxide. Fe2O3 is iron 3 oxide. Remember, Roman numeral equals positive charge on the ion. Don't forget that. Same with the next one. Copper is a transition metal that requires a Roman numeral. So Cu is copper, both of them actually. And S, the nonmetal becomes sulfide. So they're both copper sulfide, but we got to be able to tell them apart. So let's see. Sulfur's in 6A, just like oxygen. So it forms a -2 ion. Only one copper there in CuS, so the charge on that copper's got to be +2. So that would be copper 2 sulfide. Now what about the other one? Well, S is again -2. So it means the positive charge has to be +2, but we have 2 coppers. So if the total positive charge in that compound is +2, but there's 2 copper ions, then each one of them has to be +1. So it'd be +1 times 2. So each one +1, copper 1 sulfide. All right, copper 1. Okay. Let's go to the next page. Or I should say, let's advance the page. In writing a formula for a binary ionic compound, given its name, you must remember to balance the charges to 0. All right? Must remember to balance the charges to 0. So lithium in 1A has a +1 charge. Nitride, which comes from nitrogen, is in 5A. Remember, 5A nonmetals gain 3 electrons to achieve their octet. That'd be a -3 charge. Well, how many lithiums are you going to need to balance a -3? You're going to need 3 of them. 3 of them. All right, remember? So here's Li with the 1 valence electron. Here's N with 5. And lithium transfers electrons to nitrogen. You're going to need 3 lithiums, remember? 1, 2, 3. Li3N. All right? So without drawing all the bonding there, just by looking at charge, we can determine how many of each ion are going to be needed so that the overall charge balances to 0. All right, calcium iodide. Calcium's a +2 ion in 2A. Iodide in 7A is -1. Going to need 2 iodides to balance 1 calcium. So it'd be CaI2. Okay, CaI2. Sodium phosphide. Sodium's in 1A, +1. Phosphide is the negative ion of phosphorus. Phosphorus is in the same group as nitrogen. So it'd be -3. So we're going to need 3 sodiums. Na3P. All right, Na3P. Cadmium chloride. Okay, so cadmium's a transition metal. And you're thinking, wait a minute, shouldn't there be a Roman numeral in there? And the answer is no, because cadmium's one of the 3 exceptions. Remember, cadmium is always +2. Got to remember that. Chloride is -1. All right. Chlorine's in 7A, forms a -1 ion. So we're going to need 2 chlorides to balance that 1 cadmium. So it'd be CdCl2. All right, CdCl2. All right, let's go to the next page. I think we can still see it. Okay, zinc sulfide. Okay, so here again, this is I'll put a little star here. This is a transition metal exception. All right, no Roman numeral. Same with zinc. Transition metal exception. Zinc is always +2. All right. Sulfide. Sulfur's in 6A. That would be -2. Those balance. So they're gonna combine 1 to 1. So it'd be just ZnS, zinc sulfide. All right, manganese 4 oxide. Here's a transition metal. In fact, the last 4 are all transition metals. They got Roman numerals in them. What's the Roman numeral tell us? It tells us the positive charge. All right. So manganese 4 is Mn +4. All right. Mn +4 is its charge. What's the charge on oxide? Well, it's -2. All right. 6A. Gain 2 electrons. Plus 4 and minus 2. Going to need 2 oxides to balance that. So MnO2. Right? MnO2. Cobalt 2 bromide. So cobalt 2 would be cobalt plus 2. Bromide is minus 1. It's 7A. Going to need 2 bromides to balance the 1 cobalt. It would be CO Br2. That's a small O, by the way, in CO, cobalt. Copper 1 chloride. Okay, so copper 1 would be plus 1 charge. Chloride is in 7A minus 1 charge, so it'd just be CuCl. Tin 2 oxide. All right, so this is a normal little star on that one too, because this is, excuse me, this is a normal metal exception. Remember, tin and lead is the other one. They're both in 4A, but they're far enough down that group that they can form multiple ions because their coulombic force is pretty weak. All right. Remember, they can form a plus 2 or a plus 4 ion. And so because of that, we need a Roman numeral with them. So tin 2 would be Sn plus 2. All right. Oxide, of course, is minus 2, 6A. Plus 2 and minus 2 balance, so they're going to combine or bond 1 to 1. So it'd just be SNO. All right, SNO. Snow. Hopefully it's not snowing out. I don't think it is. It wasn't when I got here. So SNO for tin 2 oxide. Okay? All right, well, study these rules carefully. All right? Study the rules carefully of naming and formula writing for binary ionic compounds. Remember, these things, metals keep their normal name. Non-metals, monatomic non-metals, all right? Names change to IDE, all right? So metals name normal, that's first. Non-metals name IDE, that follows, all right? Metal might need a Roman numeral in it, all right? Well, most transition metals do. Tin and lead are 2 regular metals that do. We have 3 transition metals that do not require a Roman numeral. Remember, the Roman numeral is equal to the positive charge. All right. Silver, cadmium, and zinc are the exceptions to that in the transition metals. And then when writing formulas, all right, remember the exchange of electrons has to result in happen in such a way that the overall positive and negative charge in the compound adds up to 0. All right, so make sure you remember that when writing formulas. So I think I've given you everything you need to complete the assignment for tomorrow. So I think we're ready to go. So if you have any difficulties, refer back to this lecture, refer back to your notes, go over it again. This is very important stuff here. See, what we're doing now is we're working our way towards reactions. Can't run a reaction or write a reaction if we can't write a formula correctly. So we gotta get this down first. All right. So I think that's it for today. So until next time, this is Mr. Keister signing off. Stay safe, everyone. Take care. Stay focused and keep working hard. Polyatomic ions coming back tomorrow. Make sure you remember them. All right. Until then, see you guys. Take care.